Hi, this is Mikhail and lecture number 4. Today I have a really late lunch, as you can see, so I apologize, but this one is a better attempt at the previous one. So today we have a lecture on classification and classification quality metrics. Also we will briefly cover cross-validation. It's the way to estimate the test error of your model. So this is an easy lecture in terms of math, so we do not have statistics or complex algorithms here, but we do have several important concepts. Okay, let me start with some examples of supervised data science problems. I will give a very brief explanation and introduction to each problem, just to highlight the major aspects. So this one is the most famous data set in machine learning. It's kind of hello world for machine learning. This is a data set for classification, and within this set we have 3 classes and 50 data points. And each class, so we have 4 features, and features are really basic measurements. So we have a flower, and we measure 2 lengths and 2 widths, and this is actually in centimeters, and this is the set of features. So we have 4 features, 4 continual features, and this is our input data, or X. Our target is just the type of a particular flower. We have 3 different types of iris within this data set, and the goal is obvious. We want to build a model to identify the type using these 4 types of measurements. So this is a classification problem, and this is a so-called multi-class classification problem. We have 3 classes here. So in contrast, for some problems we have only 2 classes, and in this case we name the problem binary classification. So the next example is one of these binary classification problems. So now we have data related to a spacecraft, and we have some conditions, say wind speed, and we want to make a decision. Do we want to use automatic to land the spacecraft, or the conditions are too tough and we need to switch to the manual mode? And we have several variables. Some of these variables are continuous one, some are categorical one, like visibility, yes or no. And but still, this is a set of our features, or X, and our target variable is just, as I said, the type of this landing procedure, automatic or manual. It's a binary classification problem. Okay, the next example. It's a set of data, it's experimental data collected from a population of mice. So for each mice we have several measurements, say, as far as I remember, 15 measurements for each mouse, and within each measurement we have 77 expression levels. So in this case we have 77 features. This is these expression levels, and more than 1,000 of measurements. So one data point is one measurement for one particular mouse. And we have several classes within this data set. And actually we have two types of mice: control or healthy, normal, and trisomy mice. It's kind of the analog of Down syndrome. And this is one way to describe the targets. Also, within this experiment, some mice were stimulated to learn somehow. Some don't. This is the second label. This is the second way to define groups, define classes. And finally, some mice were injected with saline and some with memantine, so it's just two different types. And this is the third way to define classes within this problem. And obviously we can try to find the expression related to, say, stimulation to learn. We can try to find a way to predict, say, trisomy or control. And in this case, we can describe this problem as multi-label problem. So we have, in this case, we have three binary labels, and for each data point we have three labels. Or we can think that this is kind of a multi-dimensional output, multi-dimensional target. Okay, and for simplicity, we can reduce the problem and just ignore the second and the third labels and just consider the first one. And this is the case for our exercise during the seminar video. We will work with this data to play with cross-validation and classification algorithms. But by now, we can think that this is an example of as a problem with a quite large set of features. So now we have not one or two or three features, but now we have 77 features, so it's a huge table, or at least a large one. And we still want to classify our measurements into two groups. Okay, so now just to warm up, a small practical exercise related to the Titanic dataset. So just to remind you that we have a really simple but intuitive dataset. So here we have information about the Titanic passengers, some demographic information like sex or age. We have the information about the number of siblings on Titanic, and some other information like class of the or name, and we also have the column survived or not. And we can consider this one as a two example of a classification, and we can try to predict survivance based on the, say, demographic data or additional data related to class. So first class passengers are likely to survive, right? And here we need to pre-process our data to move some categorical features with string, some strings, words like male, female. We want to encode these variables using some numbers, for example 0 and 1, and this is a small example. Also we may want to drop some features like name. It's not clear how can we use name to predict the target variable, so we can just drop it. And finally we have this table. For example, we have two examples of encoding of categorical variables. So originally we have this sex variable. It was, you see, male or female, just text. And here we map these variables into 0 and 1. Then for another variable called embarked, another feature, we have different letters, C, S, and Q, as far as I remember. Yeah, Q. And this is the port where passenger go to the Titanic. So we had three different ports in England, and also for some passengers this information is not available. And we encode this as 4 binary features, and as you can see, for each passenger we have 3 zeros and 1 1. So this is a way to encode these 4 groups into 4 features, and now we can use these features as just numerical features within our models. Okay, then we can try to use k-nearest neighbors classifier. During the previous lecture we discussed how this method works for regression, and actually for classification the idea behind this method is exactly the same. We just want to find the k-nearest neighbors and then make our prediction based on the labels of these nearest neighbors. Imagine that among, say, 5 neighbors, 4 survived and 1 did not survive. Then we can predict that this our test point, the label will be survived. So this is a very simple and intuitive way to use k-nearest neighbors for classification. Okay, so here we have this just k-nearest neighbors classifier, and then we can try to fit it, but as you can see we got value error, and the reason is that for this data point, for this data set we have some missing values. So you see that we have this error message, and we can easily check that for some variables we really do have missing values, and we just need this count method from pandas. And we can see that for some passengers we do not know their age, so we can just drop this feature. We do have better strategies, but for now we can just either drop the feature itself, but it seems that it can be an important feature, right? Or we can just drop several dozens of passengers with missing age. This is not the best strategy, but this is definitely the most simple one. So for simplicity, we want to drop it. For some methods, like k-nearest neighbors, we cannot work with missing values. It's clear, because to find nearest neighbors we need to measure the distances between our test point and the training point, the whole training set. And we cannot measure this distance if some features aren't available. So for some methods we can handle these missing variables, and the most popular and powerful example is decision trees. So we'll cover this option later during the course. But for now we just drop these passengers. So you see that we have drop now method here, and axis equal to 0 means that we want to drop rows, not columns. If I change this 0 by 1, in this case I'll drop this H column, but I don't want to drop it. So in this case we just drop again slightly more slightly less than 200 of passengers of data points. And then now we can fit it, and we can try to calculate the accuracy. So the accuracy is a very simple metric. It's a quality metric, right? And here I just want to highlight that this is the accuracy on the train set. And as we know, this is actually not the right way to measure our quality. It's a way to measure the complexity of our model. And as we can see, the accuracy is just the number of correct answers. So for each data point, from k nearest neighbors, we got zeros or ones. This is the final prediction according to the rule I described above. And then we can count the number of correct answers. And in this case, the number of correct answers on the train set is almost equal to 100%. But we know that this is the wrong way to validate our models, but still we can play with the number of neighbors. At the end of the previous lecture, I asked you to think about the ways to control the complexity of k nearest neighbors, and obviously we can do it using varying this k, so the number of neighbors, and the n equal to k or n neighbors equal to 1 corresponds to the most complex model. From the first glance, it can be counterintuitive, but then you may think that if you use a really huge number of neighbors, it's at the end it can be considered as just averaging over the whole training set, or it will be just a constant fit, right? So we can play with, right now we can play with these n neighbors and say I can use 10, oops, and for some reasons I got this error. What is it? Input contains none or value. Strange. It seems that I need to launch this cell again. Yeah, it was, yeah. Okay, yeah. So for one neighbor, we have almost 100 persons, and for say 5, we have 80, for 10, 75, and say for 100, 67. I believe that 67 is close to the actual number of zeros or ones within our training dataset. So it's near to the constant fit. We can just print it. Okay, so we have 60% of zeros. Okay, well, not 67, just 60. And for example, this one, yeah. And now we have this constant fit. So now we have the accuracy is equal to the dummy classifier, which always says, no, this passenger will not survive. And in this case, we have 60% of correct answers. Okay, let me remind this illustration of how model complexity affects the train error. So we can think that squared bias is our train error, and the total error is the test error. So we just played with this train error. So we started with a very complex model with n neighbors equal to 1. So we were here somewhere. Then we jump here, here, and here at the end. So this is the last model with complexity with n neighbors equal to 100 or 300. It's somewhere here. Okay, we can try to reproduce these curves again for k-nearest neighbors and for this problem. And we need to somehow identify test samples, right, within our dataset. And the most simplest way is to do a split, so to select a subset of our initial dataset. Here I use 1/3 of the original dataset, so we can remove it from the training set and say, okay, we'll use it to test our model. And we know that this is a better way to validate our model, because it allows us to estimate that we can generalize our predictions to new unseen data. So okay, we can start again with this model. So I believe that this answer is still for the k equal to 1 and neighbors equal to 1. And then we can add the prediction on the test set, and you see that it's not terrible, but near to, it's close to this always constant answer that the passenger will not survive. And it may suggest that this contrast between this large gap between the error on the train set and the error on the test set. This gap may suggest that we need to decrease the complexity of our model. Now it seems to be too complex. And we can try to, again, reproduce these model complexity curves. This is, again, a very simple cycle. And within this cycle, I just iterate over different number of neighbors and calculate train and test accuracy. And as we can see, actually for almost all, n neighbors, we have approximately the same accuracy. So this method, at least applied directly as we do here, this method doesn't allow us to produce a reasonable curve, so it's less than 70%. I just want to try an idea. Let me spend a couple of minutes with this exercise. So what I want to do, I want to add normalization. Let me check the range. Yeah, it's describe, method describe, yeah. So as we can see, this is the way to get some statistics from our data, and we can see that we can check mean and max values, and for some features it's kind of near 0, from 0 to 1 or to 3, but for some variables, for example for age, which is obvious, we have a really large range, and for example for this one, this is fair. Actually I believe that this is just ticket price. We have a really large scale of a really large range of variables, and this range may affect the way how we find the neighbors, and this huge range may result in the following effect. We take into account, when we try to find neighbors, we take into account features with the largest range, and in this case it's fair. We may think that this is not the best choice. My feeling is that sex and age are the most important features, just from kind of a priori experience. So it's likely that k-nearest neighbors fails just because we have these different range of features. We can try right now, we can try to modify our pipeline, our classifier. Now it's not a pipeline, it's just a classifier, in order to fix this problem. I'm not sure that it will work, but we will try. Okay, what do we need? From sklearn, model selection, import, from pipeline, import make pipeline, and from sklearn preprocessing we need standard scaler. So standard scaler is the way to transform our data from this unnormalized range into kind of standard or Gaussian variables with zero mean with unit variance. Okay, how can we modify our pipeline? And let me add a new variable, scaled, and here I also want to plot scaled. The previous version, just test error without scaled, was pre-computed, so I just want to visualize it, but I don't want to modify it. So I just introduce a new variable, a new list, and I'll store my accuracy scores within this new list. And I also want to modify my classifier, and now I want to use make pipeline, and the first step of this pipeline will be transformer. We already discussed one transformer, it was polynomial features. Standard scaler is also a transformer, so it processes our features, as I said, to make the mean value for each feature equal to 0 and the variance equal to 1. Let's try. And where is the plot? It's still calculating. Okay, we need some time to go through these 50 neighbors. I suppose that it should take no more than 30 seconds. The dataset is not huge. The method is simple. Okay, let me return to this slide in a couple of minutes, and now we can briefly go through several classification algorithms. We have some utility functions, just auxiliary functions to plot the predictions for three simple problems. This is a scikit-learn example. And here we have three toy problems. In all cases, we have just two features and two classes. So red points and blue points. And we want to classify, to make a decision rule how to separate red points from the blue ones. And in addition to the just binary predictions, for many classification algorithms, we can also produce the probability of belonging to one class or another one. And here we have the original training points, so these blue and red points, and the calculated probabilities. So dark blue corresponds to, say, 1 for sure, so blue points for sure, dark red, again, red points for sure, and then, for example, these two colors correspond to probability near to 50%, so 50-50 approximately. And we have this is a linear problem. This is again likely more complex than linear problem, and this is a simple linear problem. And for all problems we have some random noise. So this is a linear problem, but we cannot separate all the points, so we have some misclassification errors on the boundary. But as we can see from this score, as far as I remember, is kind of accuracy for the test set. We have a really good classification here, and more or less good here, but here we try to use a linear method. So just logistic regression, it's the direct analog of L2 of linear model for regression. So there is some confusion due to this regression part of the name. Actually, this is a model for classification, just a simple linear model for classification. And here we successfully identify some regions with high probability of blue points and high probability of red points, and there is a region with some errors. And here we cannot split the data completely, so just kind of a random guess. So linear method is not enough here. Let me return to the results. Just interesting. Yeah. Okay, great. As you can see, now we really fix the problem. So orange curve now, I guess that we need to label it. This is our label. It's train scaled. This is test unscaled, and this is test scaled. And also we need to show the legend. Okay, so as we can see, this really simple operation, I just add this standard scalar. This operation boosts the quality from, say, 0.7 to 0.9203. I'm really glad that it helps, because this is a very important part for many methods, not for all, but for many methods. For methods that directly uses distances, like k-nearest neighbors, we need to calculate the distances before we made the final decision, and this scaling, it affects the distance, and it's better to normalize to remove this effect. For methods with L1 or L2 penalties, this scaling is crucial as well. If you have a feature with large range, then the coefficient for this variable will be low, right? Just to compensate this huge range, we need to use a small coefficient. And vice versa, if we have a feature with really tiny range, say from 0 to 0.01, and for this variable the coefficient must be high. And as we remember, L1 and L2 penalties try to reduce the absolute values of coefficients, and both methods will effectively remove this feature with small range from the model, because the coefficient must be high, but it cannot be high due to this penalization. And even if this feature is a useful one, it will be just removed. So it's a kind of a good way to use many models, including linear models and k-nearest neighbors models. Is just to use pipeline, and the first step should be the standard scaler. So this is a really nice exercise. So as you can see, we boost our accuracy really from almost random or constant classification to near perfect one. Okay, so let me return to this part. Here, yeah, this is this logistic regression, and actually, I just want to remind you these two types of penalties. We can use. Let me remove this one. We can use penalty for this model as well. We can introduce so the same way, the same penalty as we had for linear models, but the only difference is that now instead of the original parameter alpha, we now have this parameter c, and c means complexity. And this is kind of some misunderstanding within scikit-learn concepts. I prefer to use alpha everywhere or c everywhere, but these two variables are just c is equal to alpha in the power of -1, so 1 divided by alpha. Large alpha means low complexity, so low C values. Small alpha means no or almost no regularization and complex model, so large C. Anyway, we have alpha for regression models, for linear regression, and C for other models. And here we can use this penalty. We can use L2 penalty, but actually we do not see any difference right now. We can try to, okay, no, yeah, this is a simple model, right? Low complexity. Say this one, well, almost no effect. But also we can try to use L1 penalty. As far as I remember, we will got error right now. Yes, there is an error, and the error says us that some solver supports only L2 penalty or non-penalty, so just kind of a simple model without penalties. And as we discussed, almost all machine learning methods can be considered as an optimization problem. And so there is an optimization algorithm behind which tries to minimize this function and to find the optimal set of parameters. And there are different algorithms to solve these optimization problems. And this LBFGS is one of these algorithms. And it can be used only for L2 penalties, just because L2, as I said, is from optimization point of view, it's a better target for optimization than L1. So we need to select a different solver. So as we can see, to show this signature, you need to press Shift plus Tab several times. So very brief help, larger help, and even larger additional window. So here we can see that there are several solvers, and some of them support only L2 regularization. So we can use, for example, liblinear and check that now, it works, and likely due to this constant color, we can say that this penalty removed both coefficients, so just a constant model. We need to make this complexity restriction later. Yeah, for example, this one. So here, for the first problem, we have both features. You see that the decision boundary is a combination of both features, x1 and x2. For the second problem, with this penalty, we removed both features from the analysis. And finally, for the last problem, it seems that we removed one feature, which is not useful for this particular problem. This one, this feature, say x2, it was removed, and this feature is used to make the decision. So this is kind of the illustration of how L1 penalty works. Okay, great. So the next method is so-called support vector machine. We will not go deep into details, but there are some math behind this method. We will cover it later during the course from optimization perspective. We will check and we'll compare different methods in terms of their loss functions and penalty functions. But for now, we can think that this is another method, and in addition to the simple linear decision boundary as we do have here, it can be also used to create nonlinear models. And the key mathematical concept behind is so-called kernel and kernel trick. So now we have a two-dimensional space, right? So we have our two features, and for some problems it's enough, these two features are enough to solve the problem, for example, as we see here. But for some cases, for example, this problem 1, it's definitely not enough if we work with a linear model and just these two features. So we have two ways to resolve this issue. One is to use a nonlinear model. A different one is to actually it's a different view on the same concept, how to create a nonlinear model. This concept is similar to our previous experience with polynomials. What can we do? We can say that, okay, we cannot build a solution, a linear solution in this space, in this feature space, using these two features. But what if we create new features, for example, polynomial features? For example, we can use, instead of the original set of features, we can use x1 squared, x1, x2, x2 squared, so just polynomials. And obviously, in this case, this is this kernel, so you see that this is polynomial, degree equal to 2. In essence, it's very similar to our previous exercise with the one-dimensional interpolation, one-dimensional regression problem. And you can see that for at least this problem, these new features these new features work fine. We solve this problem with good accuracy. For these problems, we have some issues, and later we will try to resolve. And here, when we use polynomial kernel, we effectively move our problem from the original feature space to a polynomial feature space, say with degree equal to 2. But we can create kernels which moves our two-dimensional features into infinite dimensional space. It's hard to imagine infinite dimensional space, but from a mathematical point of view, it's obviously possible. And for some kernels, we actually do this transition from two-dimensional into infinite dimensional space. And then we apply a linear model, a linear rule in this infinite dimensional space, And in the original space, we get a nonlinear boundary, as we can see here. So if we don't want to think about this complex math behind this idea, we can just suppose that this nonlinear kernel, for example, RBF, which stands for radial basis function, is just a way to fit a nonlinear model. And here we can also play with parameter c, complexity. So now we have 10 in the power of 4, which seems to be a quite complex model. We can try to modify it and select 2. Well, it's still a complex one, but now we have less regions, small regions, for example, for this one. Or we can even say 10 in the power of -2. And you see now it's even more simple. So just one large red area here and one large blue area here, approximately the same for this one. But now we have some misclassification right here, or say, yeah, mainly here. So this is again the way to control the complexity of your model, and you can play with this parameter and you can try to find the most appropriate complexity. Okay, and how can we do it? How can we select this optimal complexity? So we know the way to control the complexity. For this particular model, we have special parameters, special parameter c. For nearest neighbors, we have n neighbors. For other models, we have different other parameters. So how can we select the best one? A simple choice is to split our data into several parts, into 2 parts: the training one and the test one. Then we can fit several models for several values of complexity parameter, as we did, for example, here. So we just try several complexities and then select the best one. Actually, we can, for nearest neighbors, we can select many, say from 10 to 30, and it doesn't matter. But for the and we need to use our test set to estimate the test error, to estimate the ability to generalize of our model. And this is a simple way, right? We need to do one split of the data. For example, we can say that we want to select 20% of our data as the test set and the remaining 80 as the train one. But the problem is that in this case, we just use only this small part of our data set to validate the model. And sometimes we want to use more data. We want to validate our model using as many points as possible. And in this case, we can do a simple algorithm. We can use a simple algorithm, which is so-called k-fold cross-validation. And this is an example of 5-fold cross-validation. So initially, we split our data into 5 parts, or k parts. And then we train, for each complexity, we train k models. For the first model, we use these 4 parts, the combination of these 4 parts as training set, and this one as the test set. Then we move our test set to the second part of the data set, to the third, and finally to the k part of the data set. And this is a simple way how can we use the whole set to estimate the accuracy or other metrics. And there are some interesting concepts behind this splitting. And for example, in some cases you need to do a random split, so not to select these consecutive blocks of data, but sometimes you need to shuffle your data before. And for example, imagine that you have a specific order of data points in your data set, and in this case you need to shuffle your data before. Sometimes you have some groups within your data set, and you want to put all measurements, all data points from one group either to the train set or to the test set. And it means that these groups must be taken into account during this splitting process. And I recommend you to follow the seminar, as we have a really nice example there related to this concept.